Hello, I'm Mr. McBrien. This is SCH4U, Introduction to Organic Chemistry. So today we're going to talk about the bonding that occurs in carbon compounds, talk a bit about hydrocarbons, and we're going to be introduced to the concept of systematic naming of organic compounds. But first, let's talk a little bit about what organic chemistry is. So one definition is that it's the study of the structure, properties, composition, and reactions of carbon-based compounds and their derivatives. So what do we mean by derivatives? Well, there are other elements that can become part of organic compounds, such as hydrogen, oxygen, halogens, phosphorus, silicon, and sulfur. And in a few other cases, some of the other elements can become important. But why is carbon so special? Well, carbon has some unique properties, or at least very exclusive properties. It can form single, double, and triple bonds, and we'll see more about that later. We can connect it up to other carbon atoms to form rings and sheets. And when we start to do these things, we can form the basis of almost every life process and many, many key products that we use every day. So even if we only consider just carbon and hydrogen, we can think of this huge molecule forming the basis of plastics. Get a little bit smaller and we can talk about motor oil. Smaller still and we've got diesel. And even smaller and we've got a major component of gasoline. So with just a few elements, we can produce all kinds of different things. So a little bit about carbon bonds. Carbon has a valence of 4. It wants to share 4 electrons, and in order to do that, it'll form 4 bonds with other elements. If we look at the classic Bohr model, the simple molecule methane has 4 hydrogens and a carbon. And we can see the shared electrons here that allow carbon to form its 4 bonds. We call these covalent bonds because the electrons are shared fairly equally between hydrogen and carbon, and we'll return to that concept later. Thank you. Here are some other structural formulas of methane. So we have our stick model down on the left, our Lewis model, and then we're going to see a little bit more about shape, because shape can become very important in organic chemistry. So here's a ball and stick model for methane, and here's a space-filling model that reasonably approximates the shape of a methane molecule. When we form 4 different bonds with carbon, we wind up with a situation where the substituents that bond to the carbon want to move as far apart as possible. They repel each other. And in order to maximize the distance between 4 components, what we wind up with is a very special angle called the tetrahedral angle. And this maximizes the distance, in this case, between the hydrogens that are assorted around carbon. That tetrahedral angle is 199.5 degrees. And this is kind of a magical angle between different components that we can detect using techniques such as X-ray crystallography. And the only time we really depart from that 109.5 degrees is when we wind up with different things attached to the carbon, such that one will occupy more space and push the others slightly to the side. And that angle, we can use that in order to decide what the size of the things around that molecule are. And in some cases, that shape becomes extremely important. Now, when we talk about this single bond or this sigma bond, there's one more very important concept that we need to cover. And that is this idea of rotation around that bond. So before we go through this concept, it's probably a good idea for us to just quickly remember that carbon molecules are in fact three-dimensional. And so we can illustrate this. We'll move across to ChemSketch and we can draw, well, let's start with a simple methane molecule. And we can look at it in 3 dimensions. And we see that the hydrogens are around the carbon in that magic tetrahedral angle. So we can look at this using our 3D viewer. We can see a space filling model like we saw previously. But sometimes it's just as easy to look at the ball and stick model. So whenever we're talking about carbon molecules, we need to remember that they're in 3 dimensions. And that applies to methane, but it also applies if we have a larger molecule. So if we have something like this, we need to remember that all the atoms are arranged in 3 dimensions. We need to remember this and keep it in mind. So this is approximately the tetrahedral angle between each one of these substituents. Hopefully that is reasonably clear. Okay, so when we draw then a carbon chain like this one, we have to keep in mind that we're representing in 2 dimensions something that is really in 3 dimensions. And we can note here our different substituents around these 2 carbons that aren't shown here. We've got an amine functionality, 2 methyl groups, hydrogens here, and another methyl group. One thing we need to realize is that this bond here, this single bond, allows for rotation with very little energy. It'll resist rotation, but not very much. And so what that means is that this molecule that we see here is essentially the same as this. So we can see the amine functionality has moved, but this is still the same molecule. We're rotating these 3 substituents at the end of this molecule around this sigma bond, which allows free rotation. And some of you will anticipate where I'm going next. What that means is that's also equivalent to the case where the amine is down on the bottom. So in this case, we're rotating around this. So whenever you're looking at these molecules in 2 dimensions, try to keep in mind that it is a 3-dimensional molecule, and try to always keep in mind whether rotation, free rotation, is possible. Okay, so even if we keep in mind that those 3 molecules were all the same one because of rotation, we can still generate a lot of different compounds. Even if we account for stability, there are a lot of different organic compounds that are possible when we start to add in those other elements we mentioned earlier. So to take things out to the extreme, GlaxoSmithKline, in their drug discovery efforts, have a library of about 4 billion molecules that are encoded onto DNA for drug screening. If we want to move into the educational sector, Harvard has a conventional library, not DNA encoded, of about 500,000 unique molecules. So there are various places throughout the world where they have these things they call libraries, and you can see why when you see this picture. Their molecule libraries are massive, all in pursuit, of course, of the next big drug discovery. Okay, so let's back up a little. When we talk about hydrocarbons, they're made of only carbon and hydrogen, and we'll sometimes talk about saturated versus unsaturated. Saturated hydrocarbons are like the one I showed a few seconds ago. They have only single bonds. But we can have, as we mentioned before, double or triple bonds, and we call these unsaturated because there could be more hydrogen than there is present. If there are double bonds, we talk about the general class as alkenes. Triple bonds, we talk about them as alkynes. We can form them into rings, and we call those cyclohydrocarbons. And we also have these things called aromatic hydrocarbons that we'll revisit later. These are called arenes, and they have at least one benzene ring. Okay, so when it comes to saturated hydrocarbons, they all have the same general formula. For every carbon atom, there are 2 hydrogen atoms plus 2. So if we have C5, by my count, we'll have H12. And if we see that, we know that it is a saturated hydrocarbon. We can draw these saturated hydrocarbons in a lot of different ways, many of which we've already seen. So on the left, you can see a case where all of the carbons are implied. They're not drawn. We just assume there's a carbon at each one of these vertices. And the hydrogens then are also implied to be there. At any end point in a chain, we'll see 3 hydrogens, because remember, the carbon has to have 4 bonds. So they can be implied or they can be explicit. They can be drawn. It really just depends on the situation. Cycloalkanes come back around and bond back to themselves, and this eliminates 2 hydrogens. So their formula is CnH2n. And here are 4 cycloalkanes right here: cyclopropane, butane, cyclopentane, cyclohexane, and in fact the rings can get larger. We can have heptane and octane and so on. Now, we've been talking about the general names for these types of compounds. There's an interesting challenge, and it's going to occupy a lot of our time over the next couple of weeks. An organic structure we've seen is a 3-dimensional artifact. And it has 3-dimensional coordinates for each atom. It has a bunch of standard components that we're going to talk about a great deal. When architects want to communicate this kind of thing, they use it with drawings, and chemists do as well, and we'll be drawing a lot of molecules. But it's not always practical to communicate molecules this way. Imagine you're on a phone conversation with someone and wanting to talk about or refer to a specific molecule. You can't always show them a picture. Of course, it's easier than it used to be. But the question is, how do we take a 3-dimensional object and turn it into a text string? How would we take a house and describe it accurately with only words? Well, that's pretty challenging. And the same kind of problem applies to molecules. I'd invite you to pause the movie for a second and just think about what ideas you might try to do to try to describe molecules like the ones we've seen in a text string. Okay, we're back. Let's talk about text identifiers. There are a whole bunch of different methods that have been devised for different applications. The first arose out of necessity thousands of years ago. People wanted to talk about given compounds, and they had no idea what the 3-dimensional structure was, or even the 2-dimensional structure. They weren't even certain that atoms existed. So these compounds had common names, like aspirin or lecithin or tartaric acid. Later on, we wanted to be able to describe things succinctly, particularly for purposes of computers, and they invented SMILES strings, which allow us to describe the skeleton of a structure. INCHI is just another kind of encoding mechanism, not very intuitive for human beings, but still a way to convert structure into text strings. Mole files are remarkable in the sense that they contain three-dimensional coordinates of every atom. But you sure don't want to see one on the screen. It's a pretty daunting thing. You certainly wouldn't be able to decipher it or read it off to someone over the telephone. And for this reason, two different kinds of nomenclature have been devised. CAS, that we won't talk about too much here, and IUPAC, that we will cover a great deal. And you'll be spending a lot of your time over the next 2 weeks thinking about IUPAC. So what is it? It's systematic generation of non-ambiguous names for compounds. So what do I mean by non-ambiguous? Well, non-ambiguous accomplishes one thing very, very well. Only one structure for a given name. What that means is if I try to patent a given name, no one can think it's a different structure. Now, the other objectives of IUPAC, we can argue about whether they achieve these things very well. They wanted to have as few rules as possible, which makes it as easy to learn as possible. And they wanted to have it easy to apply. You can argue, certainly as you learn about it, you can decide for yourselves how well they did with that part. And then the last thing that they would like to see is that there be only one name possible for a given structure. And in fact, the IUPAC rules fall apart pretty well around that objective. Why? Because there are a lot of different accepted IUPAC conventions. So what that means is two different people using two different sets of rules can correctly name the same structure with two different things. And that's not ideal, but it's one of the things we have to live with. In any case, accurate systematic names are extremely important to publications and patents. When I say that, of course, as usual, it translates into dollars. If you get the name of the structure wrong, your patent may not be valid. Now, the IUPAC naming that we do will be fairly easy, especially once you get a handle on it. It isn't quite so simple for very large compounds with lots of different substituents. And so the rules have had to be revised many times over in order to make them more accurate for and effective for different kinds of compounds. So how do we apply these rules? Well, let's just go through it very quickly. The first thing you want to do when you're naming alkanes is identify the longest alkyl chain that's available. Then what you want to do is find any additional functional groups, any additional things bolted onto the sides of that alkyl chain. Then you number the carbons, and you have to choose which way to number them. We'll talk about that a little bit, such that you generate the lowest numbers for these groups. And if there's ever a tie, you use a set of priority rules that we'll cover later in order to resolve that tie. Once you're finished, you write the names of the functional groups in alphabetical order with their numbers involved. So how do we find the longest chain? Really, all we do is we just count the number of carbons in a given chain. So this molecule has 10 carbons, if we do a quick count, but 2 of them don't get counted because they're in fact methyl groups off of the main chain. Instead, what we do is we highlight the main chain and we name the compound based on that. So 2, 4, 6, we've got 8 carbons there. So 8 carbons, we'll see later, means we name it based on octane. Okay, and the one trick you want to be sure you don't let me fool you with is bends in the molecule. Remember, we can rotate given bonds, and so we can see the structure, in this case, has a pretty good bend in it, right? Don't be fooled and just take the straight chain from left to right and count that off and say 2, 4, 6. say that this is based on octane. In fact, the longest chain involves taking a turn and going up to the top. So instead of being based on octane, this should be based on nonane, or 9 carbons. And the group off to the right will in fact be a functional group we'll account for with the other part of the name. So I just referred to 2 of the chains without defining them. You're going to be expected to be able to talk about these 10 chains effectively. So we've got methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. So there's our first 10, and of course there are more, but we won't ask you to memorize those. In terms of naming the functional groups, when it comes to just straight hydrocarbons, the functional groups are all based on the name of the straight chain piece. So instead of having ane, we have ile. So it's methyl, ethyl, propyl, butyl, pentyl, hexyl, heptyl, octyl. You get the idea. I'd invite you to ignore the iso and tert designations. We won't worry about those in this course. So when we want to put the functional groups on then, after we've identified the chain, we identify functional groups and their attachment point. And then we combine the names together. So let's try an example here. So our chain here is 2, 4, 6, 7. So if I count it right, 2, 4, 6, 7. So it should be heptane. Yep. And then we have our functional group, ethyl. And then the only thing we have left to do is to count which carbon number it's attached to. Now, don't catch yourself counting just from left to right. You need to realize that you can just as easily count from right to left. So instead of labeling that as the 5th carbon, it's the 3rd carbon, right? 1, 2, 3, yes. So we say that the ethyl group is attached to the 3rd carbon. And so this compound is 3-ethyl heptane. Okay, now for some of the larger alkofunctional groups, we have to accept that the first carbon of that one may not be where it attaches. So if you see another attachment point, you need to identify that. So in this case, we have a propyl functional group that we're going to attach in, but it's not attached from either of the 1 carbons. It's attached from the 2 carbon. So what we do is we break that propanol group in half and put the 2 in to identify where it's attached from. So in this case, we have propan 2-yle cyclohexane. Now, of course, we can attach other things. So if you're attaching a halogen, you can remove the ene from something like chlorine and add an O. And then you can have something like this. 1, 2, 3, 4, 5, 6. So this is hexane, but on the 3rd carbon, we have chloro attached. 3-chloroheptane. Sorry, hexane. Now you can have multiple functional groups, and what we do when we have that situation is we give all of the attachment points and just add a di or a tri or a tetro, whatever prefix we need. So in this case we have octane, and we can see there are 3 fluorines, so it's trifluorooctane. And then the numbers of attachment are 1, 1, 2. So 1, 1, 2 trifluorooctane. If there are 2 different or two or more functional groups, name them in alphabetical order, and don't forget to number each. So in this case, we have a methyl group and a chloro group, and C comes before M, so we have 3-chloro-2-methylheptane. So I already showed you ChemSketch for a few seconds. It's pretty impressive. It has a freeware tool for drawing and naming compounds. You can go ahead and use that if you want to do some extra practice. Keep in mind that in some cases it uses other rules, okay? So you have to keep in mind that in some cases there may be subtle differences to the way I'm going to teach you. Well, that's life. I know that it may not be the ideal situation, but you can always check things online and that kind of thing. It won't get any numbering wrong or anything like that. And of course, the tool is very powerful for doing things like naming difficult compounds. So we can see in this case, even though ChemSketch tends to put the two in the middle of the molecule, it still does a pretty good job of most of what we need it to do. And this is just a different set of rules than we're using in our classroom. Okay, in summary, IUPAC names are the way that we communicate chemical structure in the written word. They're systematic rules, and they let us communicate bonding in very complicated molecules with no chance of error in communication, and that's a very good thing. But it's going to require a lot of practice, and so you're going to need to spend a great deal of time practicing naming the varying compounds. So go ahead and read over the notes. Be sure to memorize the first 10 alkane chains that we saw in the slides, and get started on the naming alkanes worksheet, doing at least the highlighted problems, please. Thank you. Have a great night.